Empirical formula, notes, page 94, example 2. Reading through our second example, determine the empirical formula of a compound that is made up of 48.6% carbon, 8.1% hydrogen, and 43.2% oxygen. As we read through this problem, you should realize that there are some small differences compared to the first example. So identifying some of those differences, first thing I notice is that this second example is based on 3 elements, carbon, hydrogen, and oxygen, instead of only 2. The other major thing that I notice is that the starting quantities are given as percents instead of mass. And I will say that that is pretty common when given empirical data. So we will simply treat those percentages as the mass of each of the individual elements. So as an example, 48.6% carbon we will use as 48.6 grams of carbon. So even with these small differences, we will follow the exact same steps that we did in example 1 to determine the empirical formula of the substance in the second problem. So step 1, convert each element's mass to moles. So we have to convert 48.6 grams of carbon into moles, 8.1 grams of hydrogen into moles, and 43.2 grams of oxygen into moles. Since we're starting off with individual elements, in order to convert those masses into moles, we simply need to look up each element's individual GFM on the periodic table. So get out your periodic table, look at the atomic masses, round them to the nearest 10th place, and that will be our GFM for this problem. So take a look at the setup. We're going to show our work nice and neat as dimensional analysis. And according to the periodic table, we see that 1 mole of carbon is represented by 12 grams of carbon, while 1 mole of hydrogen element is represented by 1 gram, and 1 mole of oxygen is represented by 16.0 grams. So each element has a unique GFM compared to all others. Once when we have those values, simply get out your calculator and start the math. Remember, we multiply all numbers across the top, divide by any numbers down below. We do the same math with units. So you'll notice we have grams times moles divided by grams, which leads to the grams reducing to 1, left with a unit of moles. The other thing we want to try to do is maintain significant figures. So our starting mass of carbon has 3 significant digits, so we should really record its number of moles with 3 sig figs. Whereas hydrogen has only 2 sig figs in its measurement, so we should record its number of moles with 2 sig figs. And oxygen's quantity, like carbon, has 3 sig figs, so we should record its number of moles with 3 sig figs. So get out your calculators. Hopefully you have these calculated and take a look. So 48.6 grams of carbon equates to 4.05 moles of carbon. 8.1 grams of hydrogen equates to 8.1 moles of hydrogen, and 43.2 grams of oxygen equates to 2.70 moles. So each element's mass has been converted to moles. The second step is we need to divide each of those calculated mole values by the smallest mole value. So I hope that you recognize right away that oxygen's mole value of 2.70 is the smallest out of all the mole values calculated. So show your work nice and neat, and notice that each element's individual mole value is being divided by the 2.70 moles, which is the smallest mole value in this problem. And when you do this math, notice that it's moles divided by moles, so they reduce to 1, and we are left with a unitless number. Once when all units reduce and are gone, then we realize that it becomes a ratio. So take a look. Our mole ratio between carbon, hydrogen, and oxygen is a 1.50, a 3.0, and a 1.0. So the next step is to use those calculated mole ratios to write the empirical formula with correct element symbols and our calculated mole ratios. So this initial calculated empirical formula happens to be C1.5 H3O1. But you should have realized or noticed that the empirical formula is not a whole number ratio. We're not supposed to have decimals in our subscripts. When this happens, you will need to double all the subscripts in the empirical formula. So simply multiply each subscript by 2 to get to the best and final whole number lowest ratio. So for our final answer, going from carbon 1.5, hydrogen 3, oxygen 1, multiplying through by 2, our best final empirical is C3H6O2.